Welcome back to some more geometry. Today, we're moving on to chapter 11, talking about areas of quadrilaterals. Now, first off, what is a quadrilateral? That's a good question. Quadrilaterals, if you remember, are a four-sided figure. So anything with four sides is what we're talking about today. So our first shape that we're talking about is a parallelogram. Now, what makes a parallelogram a little special? Good question. Both pairs of opposite sides are parallel. Now, if you remember back in an earlier chapter where we were talking about our shapes, we talked about how not only are the opposite sides parallel to each other, but also congruent in a parallelogram. So the two bases right here are congruent to each other, and the two other sides are congruent to each other. Now, what's important when it comes to area of a parallelogram is that we got to understand what are we calling the base and what are we calling the height. Now, the base can be either the long sides or the short side, depending on how you have your parallelogram. What has to happen, though, is the height has to be perpendicular to those bases, whether it's inside the parallelogram or outside the parallelogram. So there'll be problems where they'll tell you a number right here. Let's say they'll tell you this is 13. They might tell you this right here is 12, and you got to find the height, maybe using a little Pythagorean theorem, or they might even give you an angle. You have to do a little trigonometry here like we did. But the height can exist outside or inside, but what has to be true is that it has to be perpendicular to our bases. So, for example, back when we first started this, I'm missing a slide, y'all. Where'd it go? Anyways, all right. So, for example, if we were looking for the area of this right here, all right. Oh, here it is. Never mind. We're gonna go back real quick. All right. So in right here, when we look at the area parallelogram, we're just taking the base times the height. Now we're used to seeing our parallelograms like a square or a rectangle right here. But so most of the times the height were the sides because they were perpendicular all the way around. So we could do base times height, get 25, or base times height right here, get 45. So in this particular problem, doing the same identity here, we're going to take our base, in this case 6, times our height right here, which in this case is 4. So since we have our base of 6 and our height of 4, we'll get 24. So we just multiply the base and height. Okay, but sometimes you'll run into problems where you don't have the height. A lot of bad habits here is that we want to take whatever side because we're used to taking length times width, base times height, and we like to call that the height because it's the side. Because in previous ones, the side has been the height. But these parallelograms are not. So we look at this right here, and they give us a side of 10, but we need the height right here, this dotted line. Now, we just spent some time doing special right triangles, and hopefully you recognize that if there's a 90 degree right here, there's a 90 degree right here. Now that's a 60. This is a 30. You start recognizing these 30, 60, 90 degree triangles. So to find our height, instead of trying to do a little bit of trig, we can actually use our special right triangles and kind of go backwards. Now, the relationship is all based off this bottom side, the short side. The short side, we remember to get from the short to the hypotenuse, we multiply times 2, and to go from the short side to the long leg, we multiply times radical 3. So to go backwards, seeing as we have the hypotenuse, we'll divide by 2 and get 5, and then multiply by radical 3 and get 5 radical 3 for our height. Now, unless it tells you to round, try to keep this in radical form. We're going to take our 5 radical 3 times our 15, and we end up having 75 radical 3, and this is area, so it's units square. All right. Another part to these right here is they threw in this postulate called the area addition postulate. This postulate is said like, hey, if you have some weird shape place, you got to find areas. You can divide these into smaller shapes, smaller parts that you recognize. For example, here we got a bunch of squares or rectangles. So let's kind of individually find the area of each one. So here, 1 times 1 is 1. 1 times 2, 2. This is a 2 times 2. We know it's 2 because there's a 1 right here and a 1 right here. So that makes it 4. This is also 2 by 2, so it's 4. This one right here, if that's 1, and then from there is 1, and then from there is 1. So the whole thing is 3, and then 2 and 1 is 3. So it's a 3 by 3. That gives us 9. And this whole thing is 5. So this is 3, this is 2. Now this is where a lot of confusion happens. This is the whole thing is 11. Well, since this is 1 right here, making it from here to here, 10. Giving the whole thing 20. You add it all up, you end up getting 40 units squared. All right, so let's go ahead and talk about Now, the next quadrilateral are trapezoids. Now, trapezoid, again, it's quadrilateral, but this time there's only one set of parallel sides. Those are our bases right here. Those are for sure will always be our bases. Unlike the parallelogram where it can turn and you have different bases every time, here, the bases are pretty set. The other parts are called legs. Now, an isosceles trapezoid, very specific type of one, has congruent legs. So the legs are congruent to each other. Let's look at the formula for this. So the formula for this one is base 1 plus base 2. It doesn't matter what you call the base. So what does matter is which one you call base 1 and base 2. You just know that those two are the bases. So you're going to add the value of the two bases, and then you're going to multiply times the height, but then you're going to divide by 2. So even though it gets turned sideways here, the two parallel sides are our bases. So our 9 and 14 here are our bases. So we'll do base 1 plus base 2. Now, what part's the height here, class? The 12 or the 13? It's the 12, because remember, it has to be perpendicular to the bases here. So times 12 over 2. Okay, add like terms, you get 23 times 12 over 2. I'm going to reduce this because I'm going to do this by hand. 23 times 6, that gives us 138, and this is unit square. Now, area equals our formula. So what did they give us the area, and we're looking for part of our formula, like this h? Well, we'll set it up as we're looking for the area. So we got area equals base 1 plus base 2 times our height divided by 2. So a lot of people want to multiply by 2. You can do that way. I'm going to do a different way. I always like to simplify first. So I got 50 equals 20h over 2, and the 2 goes into 20. Turn that into a 10. So I got 50 equals 10h. We divide by 10 both sides. 5 equals h. That's our height right here. Hopefully you paused and did that on your own. Our last set of quadrilaterals, let's look at this, is a kite and a rhombus. I bring them together because they're very similar. There's a small difference. So here, it's just a quadrilateral, meaning there's no unique thing to it. But what is a little bit special is that our sides are congruent right here. So these two sides are congruent to each other, and then the two longer sides are congruent to each other. We do have these dotted lines. They usually aren't there. I put them there. They're called diagonals, as we'll talk a little bit more about them. Here on a rhombus, it is a parallelogram, so opposite sides are parallel. But on this particular type of parallelogram, all four sides are congruent to each other, so it's really cool. And now, when the diagonals intersect, they form right angles at their intersection. So here you got 4 right angles all the way around. So I'm going to just put 1 because understood. You have 1 right angle, you have another angle, and all 4 all the way around. So the formula for this, look at this one right here. So both the kite and the rhombus are done the exact same way. Diagonal 1 times diagonal 2 divided by 2. So that's what D1 times D2. People ask, which one's D1, which one's D2? It doesn't matter. Once you can call this one diagonal 1 and this one diagonal 2, or vice versa. This one diagonal 1, this one diagonal 2. It doesn't matter. It's the line across. Now let's talk a little bit more about the diagonals because you're going to run into a problem here a bit. So these diagonals, as you can see, on a rhombus, so this is our rhombus, the diagonals bisect each other. That means when they intersect right here in the middle, they cut each other in half. So the two segments of the same diagonals equal each other, and two segments of the same diagonal equal each other. But on a kite, only the small one is the one that's cut in half. The long one is not cut in half. And it's pretty obvious that this side right here, this part, the top part of it, is a lot shorter than the bottom part. So let's kind of try this out. So here we have a rhombus that's 3. That AO is 3, DO is 4. We got to find the area. Remember, we need the entire diagonals. We need diagonal 1 and diagonal 2. Well, like we said earlier, if this is 3, this part over here is also 3. And if this is 4, this part over here is also 4. So that means the entire diagonal, that looks like a 2, the entire diagonal is 6. And then this entire diagonal is 8. So now we do our formula. Diagonal 1 times diagonal 2 over 2. We get 48 over 2, so we get a grand total of 24 units square. Now the next question is asking for the perimeter. Oh, so now we got to find this height, the sides right here. Well, we asked how did we find that? Again, we have a right triangle right here. We have a right triangle, and two sides of the right triangle are 3 and 4, making the height, the long side is our hypotenuse. So when we set up to find this problem, we'll take 3 squared plus 4 squared. We're kind of bringing in our Pythagorean theorem again, equals our c squared, making these values our c's. We've got to find what those are. And they're all the same because they all have 3 and 4 as legs, and they're all right triangles all the way around. So we end up getting 9 plus 16 equals c squared. So then 25 equals c squared. And we square root both sides. So we end up getting 5 equals c. So if our sides are 5, what is our perimeter, class? Yeah, it's 20 units. There we go. All right, let's look at our kite here. So in this particular problem, it says the diagonals of a kite, one diagonal is twice as long as the other diagonal, okay? And we know the area. So the area of the diagonal is 400 meters, square meters. So right now, if we set up the formula, it's 400 equals diagonal 1 times diagonal 2 over 2, okay? So let's kind of draw those out. They're talking about this diagonal and this diagonal. Now, I'm going to say, all right, so the length from here all the way down, this length right here, we're going to call that x, because then the other from this tip right here all the way across, this is going to be twice as long. So if we're calling this x, what should we call this, class? 2x. Yeah, it's 2x. So now we replace this d1 and d2 with this right here. We got 400 equals x times 2x over 2. Let's go ahead and multiply this. X times 2x, we got 400 equals 2x squared over 2, and our 2's cancel out. All right. We end up having 400 equals x squared. Well, to find x, we're going to square root both sides. Square root. We end up getting x to equal 20. So if this is 20, our other diagonal is twice that, 40. All right, y'all. Hope that helps. Have a great rest of your day. Bye.